All right, hello. In this video, I'm going to be working the 2023 Calculus BC free response number 6. And I'm not familiar with this problem. They just released it. I'm just looking at this for the first time. So they're giving us f of 0 equals 2, f prime of 0 equals 3, a formula for f double prime of x, and a formula for f triple prime of x. Interesting. Okay, find the fourth derivative of f with respect to x. Got a little bit of implicit differentiation. This is different. Yeah, kind of like this. This looks fun for me. I'm not sure how y'all felt about it. Doesn't really matter so much how you felt about it as how you did on it. So the fourth derivative of f with respect to x, we're going to have to take the derivative of f triple prime. Okay, so f's fourth derivative of x is going to be, I'm going to have to use the product rule. I'll take the derivative of negative 2x first and leave f prime of x squared the same. Then I'll add in, leaving negative 2x the same, taking the derivative of f prime of x squared. So we'll take the derivative of the outside, leave the inside, find the fourth derivative of f with respect to x. Okay, I think we're going to have to say in terms of f double prime, because I guess we can make the substitution eventually. Yeah. I think this is going to be enough. So I'm never really sure about the series question free response. Like, what are we justifying? Okay, but we're taking the derivative of f prime, leaving the inside the same, and then multiplying by the derivative of the inside on the outside for the chain rule. Okay, and I'm going to stop there. Okay, now if we write the fourth degree Taylor polynomial for f at x equals 0, so I know that it's like f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and f's fourth derivative at 0. And what I'm going to do, I'm going to just kind of make a roster of my derivatives. They said that f of 0 is 2, f prime is 3, f double prime is negative f of 0, okay, so negative 2. F triple prime is negative 2x times f prime. Well, negative 2 times 0, okay, that'll be a 0. And f's fourth derivative would be, okay, that's going to have a 0 in it because of these x's. So really, it's just going to be negative 2 times f prime. So that's going to be negative 6. Oh, very interesting pattern here. I'm sure there's more to be taken from this. But if we're just writing the fourth degree Taylor polynomial for f, okay, I'm going to say it's f of 0 plus f prime of 0 times x plus f double prime of 0 divided by 2 factorial x squared, f triple prime over 3 factorial x cubed. We don't really need to have it in there. I'm just like really showing off to the reader like, hey, I know how to write down a Taylor polynomial. Plus f's fourth derivative over 4 factorial x to the 4. And then that'll be good enough for us, right? That's a fourth degree polynomial. We've shown the work that led to our answer. All right, the fourth degree Taylor polynomial for f around x equals 0 is used to approximate f of 0.1. Okay, given that the absolute value of f's fifth derivative is less than or equal to 15 on the interval we're interested in, use the Lagrange error bound to show that this approximation is within 1 over 10 to the 5 of the exact value. All right, so I'm going to slide this over here and say, all right, for part B, we're doing a Lagrange error bound. So what I always tell people to do is like write down all the stuff you know. The centering point, if it's a Maclaurin polynomial, or if it's centered at x equals 0. Okay, we are approximating at x0 equals, what was it, 0.1. Yeah, we're trying to approximate f of 0.1. And then the degree of polynomial that we used is the fourth degree polynomial. It says the fourth degree is used to approximate f of 0.1. So the Lagrange error bound is given by, okay, the maximum of the absolute value of the next derivative. Okay, so the maximum of the absolute value of f's fifth derivative on the interval between the centering point and the point we're using for approximation, so on the interval 0 to 0.1, divide by that factorial, the next factorial, times the absolute value of the difference here, 0.1 minus 0 to the fifth power. Okay, and then they told us that the maximum of f's fifth derivative on the interval 0 to 1/2 is 15. So that also means that 15 is going to be greater than or equal to any value of f's fifth derivative on 0 to 0.1. So I'm going to use that 15. So I'm going to say less than or equal to 15 over 5 factorial multiplied by 0.1 to the fifth. Well, that's 10 to the fifth in the denominator. Okay. And 15 over 5 factorial, that's something I can cancel off, right? 15 is 5 times 3, so I just lose the 3 and the 5. So I think I would have 4 and 2. And then this number is definitely less than 1 over 10 to the 5. So I think, honestly, as Lagrange error-bound problems go, this one was pretty friendly. I'm glad to see that it wasn't too difficult. But I don't think that Lagrange error-bound is as hard in AP Calculus as alternating series error-bound, because you don't have to justify your answer as nicely. They usually just kind of give you that maximum of the next derivative, and it's not too bad. And I think I did a slightly better job of convincing the students in my class this year that Lagrange error-bound is actually not something to be scared of. So now the last thing is let g be the function such that g of 0 is 4 and g prime is e to the x f of x, right? The second degree Taylor polynomial for g around x equals 0. All right, I'm going to need some space for this one. All right, what I'm going to do is I'm going to copy in my polynomial for f. Because I can see where this is going, and I know they only want a second degree Taylor polynomial for g. I don't need anything past x squared on here. I'm feeling like because they gave us the derivative, I might not even need the x squared, but I'm just to play it safe, I'm going to go to degree 2 in f and to go to degree 2 in e to the x. So I think we're going to zoom in and say, all right, e to the x is 1 plus x squared over 2 factorial. So I'll call that 1/2 x squared, and so on. Right? It keeps going. But we don't really need anything more than that, because when we go to multiply e to the x f of x to get g prime, we're just going to set up for some pretty big distribution, but not that big. 2 plus 3x minus x squared multiplied by 1 plus x and plus 1/2 x squared. Okay, so 1 times 2 is 2, 1 times 3x is 3x, and 1 times negative x squared is negative x squared. 2x here, 3x squared, negative x to the third. Well, that's going to be outside of the bounds of what I need for a second degree Taylor polynomial for g, right? This is g prime, that'd be third degree, so it's too much degree. All right, and 2 times 1/2 would be 1x squared, and then these are like who cares terms because the degree is too high. So g prime, I'm just going to kind of collect all of these. 2 plus 5x. And then 3 plus 1 is 4, minus 1 is 3x squared. But I really don't even think I need that, right? Because when I go to get g, by taking the antiderivative, I'm going to have some constant plus 2x plus 5/2 x squared. Right, and then this would go to a 1x to the 3, but I only want the second degree polynomial for g, so I'm not going to be doing that. I do need to figure out the value of c, but they told me that g of 0 equals 4. So we know that there will be more terms for the polynomial for g, but they'll all have just x in them. So when I plug in 0, all I'm going to get is c. So that means to me that c equals 4. So I'm going to say the second degree, still visible to you, yes. Second degree polynomial for g is going to be 4 plus 2x plus 5/2 x squared. And that's the Taylor series problem for this year. That's it. I don't think this one was so bad. I do think that, like the stakes were pretty high. If you didn't get part A, it was probably going to be hard to get part C. But I bet that part C, there was a point for knowing the terms of e to the x. And that's something that I know that pretty much all of my students knew. And I'm hoping that y'all at least got that point. If you got nothing else, get the point for the knowing the terms of e to the x, because that was something simple to know and we knew it. Okay, so that's all for this video. Thanks for watching.